are on Module 10 now. We'll be looking at solutions. Now, there's not a whole lot new today. There's one really big new concept, but it's just really similar to what we've already been doing, all right? So nothing to be frightened about. And I don't like to make promises, but we might get out early today, all right? Because it's a little bit, actually the module's actually a little bit shorter. Even when you're doing your reading, you're going to see it's pretty short, yeah. So that's kind of nice, yeah. All right, so we are looking at the chemistry of solutions. We know what solutions are, right? We've been talking about them this whole time. So let's get a few definitions down. That's going to be your first couple of blanks in your lab book right here. So a solute, some people pronounce it solute, like to salute someone, but it's a solute. That's something that's being dissolved to make a solution. Okay, so if I'm going to put sugar in my tea, the sugar would be the solute, and the tea would be the solvent. Okay, the solvent. The substance in which the solute is being dissolved. Okay, so really very commonly for us in chemistry, our solvent is going to be water. We're going to be dissolving stuff in water. We did a couple of those, solubility experiments, what dissolves in water kind of a thing, and we saw that lots of stuff dissolves in water. Oil was the one thing that did not, right, in our little experiment. A solution is the result of one or more solutes being dissolved into a solvent. So that's the official definition. And solubility is the maximum amount of solute that can dissolve in a given amount of solvent. Okay, so that is solubility. Sometimes we'll use that word solubility as well to say if something can dissolve. If something is soluble, it can dissolve in there. Oil is not soluble in water. But salt is, right? All right. So we're going to be looking at these. We've already looked at them, really. We're going to key in on them and focus in on them, and then do one more little. We talked about molarity last time, and that's about a concentration of certain things. We're going to be looking at concentrations specifically with these solutes and solvents today. All right, so if I have a solvent here on the left, it's my beaker full of, looks like water. I have 100 grams of that weighed out there, and then I have my solute, some sort of red solid, and then I'll dissolve, it's 10 grams of that. I'll dissolve it into my, to make my solution, and notice I've not lost anything along the way because of the conservation of mass. We know that from way back in the beginning. And also keep in mind the phases of matter. We have solids, we have liquids, we have gases, and those are the three commonly found phases here on the Earth. There is also a fourth phase. It's called plasma. That's what's in the sun and in your TV set, right? So, so that's another phase right there, and it's kind of a weird liquid-gas mixture kind of a thing going on there. All right, so the solid will hold its shape. The liquid will take the shape of its container, but it does have a fixed volume. The gas will take the shape of its container. Think about maybe blowing up a balloon. All right, that would be the container that it was in, and it takes on the volume of whatever the container is. In other words, it fills it out completely. Notice the liquid right here doesn't fill out that thing completely because it just has a certain amount of volume, but the gas will. All right, so our solid can be turned into water by melting it. We'll be talking about melting points today and boiling points, turning it to a gas. Okay, if I want to take a liquid and turn it to a gas, I have to boil it. And so we have certain elements have very specific boiling points and freezing points. In fact, most, when you get to college and you take chemistry, yeah, if you have to, you'll get a better periodic chart of the elements. So the one I have from college has all of the boiling points, the freezing points of every single element, all on those little squares inside the periodic chart of the elements. So each element is different. And then, of course, each molecule is different. One of the highest boiling points that we know out there is water, and it's 100 degrees C, which is also 212 Fahrenheit. So we'll be looking at that. But what happens essentially is that we get, the solid gets disrupted by something, in this case water. The water can sneak between the particles, and when it sneaks between them, that is when it becomes dissolved. It's a liquid now. All right, so here it is. Here's my solute, here's my solvent, and the water's going to get in between, and they're going to dance around in between the water molecules right there. All right, so my solute, my solvent, my solution. All right, this is a little chart. I may have skipped ahead a little bit, did I? Or is this the next thing on your book? Okay, good. All right, so this is telling us how the solutes will dissolve in liquids. So if I have a solute that is a solid, let's say solid salts that they're sticking in the water right there, here's what happens. The requirements are this. The solvent molecules must be attracted to the solute molecules so strongly that the solvent molecules can get between the solute molecules, creating ions typically, and pull them far apart from each other. So is that just a big old blank, or do you have blanks to fill in? Okay, so here's what you might see. Can you tell what I did in bold? Molecules can get between the solute molecules. That's what I want you to write down. Pulling them apart. So I think that's the key, pulling them apart, separating them. Y'all need more light? You want that light on in the back? You can turn it on if you need it. You could open a shade in the window. It's up to y'all. All right, so the solid will dissolve. It's got to be attracted. So like if I put this solid pointer thing in a beaker of water, is it going to dissolve? No, it's not going to dissolve, and that's because the molecules are not being pulled strongly enough apart by the solute. By the solvent, okay? Now, if it's a liquid, this is a little easier. The solvent molecules need only to be attracted to the solute molecules a little bit, because the solvent doesn't need to be separated as much, okay? So the solvent merely needs to get in between. So on that one, you can just say solvent gets in between. So you can imagine putting two liquids together. Now, we may think about, it has to be soluble, right? Don't think about like oil. Oil wouldn't do it, right? But as long as it's soluble, it'd be pretty easy to get liquids to dissolve in other liquids. Now, gases are a little different. The solvent molecules must be attracted once again, and to pull the solute molecules closer together. Okay, so if I'm going to dissolve a gas into a solvent, so a gas, let's think about making Dr. Pepper. All right, I'm going to dissolve a gas into that Dr. Pepper. That gas is called carbonic acid, and it's going to go in, it's called CO2. It's going to go in there and make carbonic acid. And I need to actually pull those molecules closer together. In fact, what we do to make Dr. Pepper is we put it under pressure. That's why when you open it, okay? We put it under pressure because guess what? It's going to be pulling those gas molecules closer. And then they can be dissolved into the liquid. You get it? Yeah. So that's how that works. So the big thing is far apart, close together. Okay? All right. Dissolving ionic compounds. Easy breezy because we're talking polarity here. Okay? Especially if I'm going to dissolve something ionic in water, that's going to be easy to do because water is polar. The polar nature of water, the fractional charges on the water's hydrogen and oxygen atoms can pull apart the solutes. All right, so we remember that about water. It's polar. We've bent water, right? All that kind of stuff. We've messed around with water. We used our magnets and that kind of thing. So you can see my negative and positive charges right there. That shows that water is sticking to itself. So water really holds on to itself really well. But those are just little hydrogen bonds right there. So if I'm going to put something in there, let's say some salt. Here's my solid little crystal of salt. I can pull those sodiums and chlorides apart by attracting those positive ends of my hydrogens to my negative chlorine and my negative ends of my oxygen to my positive sodium. And therefore, it's just between those. I've now created ions. I have the ions of sodium and chloride, and the ions will conduct electricity now, this kind of thing, right? They'll taste salty. Yeah. Did y'all hear about the terrorist who tried to go poison the water hole? I don't remember what city it was in. It happened this morning. He got caught jumping into the water treatment plant of some city, and he was going to dump stuff into the water to make the water poisonous for everybody, but they caught him, And the news, they said, yes, and it was terrible. He was going to dump a whole lot of sodium chloride into the water. And she said, better known as lye. And I said, okay, well, sodium chloride is salt. No. So she was supposed to say sodium hydroxide, which indeed is poisonous. We've used sodium hydroxide before. We're going to use it next week, too, as we're going to be looking at it in a exothermic reaction. So, cool stuff. Anyway, they caught the guy. The water is safe, so you can drink the water. Sometimes we put water in there ourselves, like in a pool and stuff like that, to help with hardness of the water. All right, so here's table sugar. It's also going to dissolve because now it's a covalent molecule, so it's a little different, but it's a polar covalent molecule. Remember we talked about polar covalent and purely covalent? So polar covalent molecules can dissolve in water because they do have that partial charge that forms here on the end, and they can then be separated by our polar water right there. That's why sugar, being a covalent molecule, will dissolve in water. There are purely covalent molecules like oil that will not dissolve at all because they don't have anything to pull it apart. The water can't get in between it. All right, so if the water can't get in between it, it can't dissolve. All right, solubility, the maximum amount of solute that can dissolve in a given amount of solvent. You already wrote that down. And you can see right here, if I've made a solution in my first tube over there, and then I keep adding, y'all probably remember this from when you were little and you go to the restaurant, you'd be putting your sugar in your tea, and you're stirring it and stirring it, and finally you get to this like cake of sugar at the bottom of your glass, and no more sugar will go in there. I said when you were little because you don't do that anymore, right? Yeah, you don't put that much sugar in there anymore. And that's because what happens, you reach something called a supersaturated solution. All right, so no more sugar could go in there because it's saturated. So we'll be looking at that right here. You can see our suspension in the middle thing right there shows that if I'm trying to think of, like, Italian salad dressing. And if you shake it really well and it all looks the same like that, that's a suspension right there. Sometimes it doesn't last, it settles out and the oil separates and this kind of thing. But that would be our suspension. And then if we have our tea with all that sugar at the bottom is called our precipitate. Okay, it precipitated out, it rained out in there. And then the tea part would be called the supernate or the supernatant. And that's the part we'll be using. Sometimes you'll have a lab that'll say, use the supernatant to do such and such test. That means you're going to get the liquid portion and not get any of the solid portion down at the bottom. All right, solubility depends on the identity of the solute and the identity of the solvent. No duh. Okay. If a saturated solution is a solution in which the maximum amount of the solute has been dissolved, that's saturated. That's when I just have a couple of little grains of sugar at the bottom of my tea glass. The precipitate would be the process by which the solid solute leaves the solution and turns back into a solid phase. And it seems to me like in some of our experiments that we did in our little chem plates, remember you added some things together and something, I told you it would crash out and there was a little solid formed in there. I remember that one that was kind of a gloppy blue thing. Y'all remember what I'm talking about? Yeah, one of those things. That's forming a precipitate, and that shows you that a chemical reaction has taken place. And oftentimes we call that crashing out. It crashes out. Sometimes chemical reactions produce that. If it's just dissolving and you got to a supersaturated solution, then you'll also have a precipitate there. Hey there. All right, so here I'm just showing you once again, I'm adding a solid to a beaker. In this particular case, I'm putting in 30 grams of sodium chloride into 100 milliliters of water, which gets me to an unsaturated solution. But if I try to put 40 grams in there, notice on this right lower beaker here, you'll see a little bit of the salt right there collecting at the bottom, a little bit of precipitate. That's just showing me I have my saturated solution. And if I keep adding salt, it will not dissolve in there. It'll just start collecting on the bottom as a sediment down there. So, can you think of a way I could get that salt over here to dissolve in the water? There is a way. Can you think of it? The way I could get it, Sarah?
Put it under pressure?
That might work. Yeah, if we put it under pressure is what she said. Putting it under pressure. If we were talking about a gas, it would work really well for a gas. But for a solid, I could add, you're saying it. Yeah, heat it up. I could add energy. To it. And so this brings us back to tea, because do you know the difference between sweet tea and sweetened tea? We've talked about this? Sweet tea and sweetened tea. Sweetened tea is when you go to the restaurant, you add your sugar into your iced tea, and a certain amount goes in. Sweet tea is when they add the sugar in while it's brewing. In other words, it's hot. So guess what? More sugar can go in. So if you tasted them side by side, sweetened tea and sweet tea, they're different tasting. There's kind of a different that takes. I kind of like sweet tea. sweetened tea I don't like at all. So when I go to the I don't put anything in my tea. I just drink it straight, you know. Same with my hot tea. Yeah. So but I do kind of like sweet tea. Yeah. And there's more chemistry going on there. All right, so here's my unsaturated solution. I'm just starting to put stuff into my my test tube over here. Then it gets saturated. I get a little bit of collecting at the bottom. That's when I know that I'm saturated. You could get to perfect saturation and have nothing down there, but it's kind of difficult because you don't know exactly that you're there yet. If you see that teeny bit, then you know you're saturated. And then when I get to my super saturated solution, lots of crystals are forming down there. And this particular beaker shows over here, they're kind of changing their crystalline shape, which is true. They'll kind of dissolve and then reform there. All right, solubility and temperature. These, I believe, you only have to write down the underlying things here. For solid solutes, solubility increases with increasing temperature. So that's what I was just talking about with the sweet tea. Can increase my temperature, I will increase my solubility. The solubility of liquids are not affected at all by increasing temperature. Oh, look here, the solubility of gases decreases with increasing temperature. And we're going to do that next week. You probably know this. If you've left your can of Coke sitting in the sun, it's going to go flat quicker than the can of Coke sitting in the fridge. All right, an open can of Coke sitting in the fridge. Okay, it's got to be opened already. So the increasing temperature will cause the solubility of gases to decrease. If I heat up Coke, Dr. Pepper, if I heat it up, those bubbles will come out quickly, very quick. I'll make it go flat really quick if I heat it up. Yeah, here we're showing it. We'll do this next time. We're going to put our Coke in cold water and hot water, and we're going to see the difference. It'll look like it's boiling, but it's not boiling. It's just the gas coming out. Yeah, not hot at all. Solubility and pressure. Let's see. Increasing pressure increases the solubility of gases. And look here, it does not affect the solubility of liquids or solids. That answers our question right there. It does not affect the solubility of liquids or solids, only gases. Turn the page. All right. So here we're looking at why pressure helps with gases. So this is making my Dr. Pepper. If I put it under pressure, I force more of those gas molecules down into the liquid. I force them down into there. And that's why that's why we put them under pressure. That's why liquid propane is under pressure. Keep it liquid so it doesn't go to gas. All right. What is this? Okay, here we go. Is it a good idea to mix unknown solutions together? No. Never. We make stinky smells like last week, someone. We shall remain nameless. We made some stinky smells, mixing things together after not being told. Don't ever mix things together. Chances are there could be a serious problem. Like, for instance, if you're cleaning the bathroom and you're scrubbing and you put some like ammonia in the toilet, or when you're scrubbing and it's not working, so you bring in another toilet into another base, that can create some noxious fumes that'll hang around on the floor and knock you out and kill you, possibly. You're never supposed to use two bases together, so be careful when working with, especially in chem class. Fortunately, we are using very, very small amounts, right? We're here when we use our low chem plates. All right, so types of chemical reactions. We're going to be looking at these next week. They're kind of fun, actually. Endothermic reactions absorb energy. And so if it's absorbing energy in a beaker, for instance, and I put my hand on it, it's going to absorb the heat from my hand, which is going to make it feel cold. All right, so they feel cold. Temperature will decrease. An exothermic reaction releases energy and will therefore feel hot to the touch. And it says here, most solids will dissolve endothermically. I just think it's not really noticeable in most of them. Some are. If we used a thermometer, you could tell, but you wouldn't necessarily be able to tell by the touch of your hand. All right, so that kind of surprises me. You'd think it'd be exothermically, but it's endothermically according to your book. Which brings us to, have you ever seen these? All right, that's chemistry. Okay, we break something inside of there. You know what? I have these ones that I gave my husband for Christmas. It just has a little disc in there. Have you seen this? And you just pop the disc and it creates friction and it causes crystallization to take place and that heats it up. And then you boil it in the water and it goes back to new and you can use it over again. It's kind of cool. Maybe I'll bring that next week to show y'all. It's not chemistry there. It's physical change because it's using friction to do that from that little snapping of that metal piece. Maybe there's some chemistry. I'll have to look in to see if there's some chemistry with the metal after the fact. Was everybody okay? Did everybody get what they needed from this page? Okay, slide. All right, so now we're turning over to 10B. See, that was not bad at all, was it? That's pretty cool. Now we're gonna, we're gonna put the math part in now. Okay, so boom. All right, so these are some formulae to remember, and I'm actually gonna write them on the board. Y'all have them on your book right there? We just need to use them. So, I don't want to forget them. And I will, that's my, specialty. Okay, so the first one is, remember what big M stood for? Who remembers? Molarity. Number of moles divided by number of liters. Okay, and this is very helpful. We're just going to move this around now. So now we're going to say that way I can get moles if I multiply M times liters. I'm just going to call that L. And then I can get number of liters if I divide moles over molarity. And we're going to need more room for other formulae here in just a minute. Okay, so this is nothing new. This is what we learned last time. And so I have a little star here to say, let's write that down. That was reminding me to write it down on the board because I need it. And so we're going to do, I think we're going to do a practice one. It's really something from last module. Okay. This is example 10.1. A chemist wishes to make calcium carbonate by using this chemical reaction up here, all this. Okay? Now, one of the things you have to really remember about this is our polyatomic ions. Don't forget your polyatomic ions. Okay? Remember our chart from last time. Yeah. If the chemist mixes 50 milliliters of a 1.2 molar Na2CO3 in excess of our calcium hydroxide, how many grams of calcium carbonate will be produced? Okay, so it seems to me this is already balanced, is it? Yeah, it is. Okay, it's already balanced. First thing we're going to do is convert to liters because we know we need liters up there for our formulae right there. So it's 0.05 liters. That's easy enough. And now we're going to get from volume and concentration to moles. So now I'm going to find moles. What am I asking for? How many grams of CaCO3 are going to be produced? All right, so if I find my moles of Na2CO3 by using this right here, this is so cool. All I have to do is use this formula right here. I don't have to go to my chart or anything. I just use my molarity to get me there. All right, so I'd say my molarity is given to me 1.23. My liters are given to me. We're going to do it in liters there, and we come up with 0.065 moles of Na2CO3. Now, how does that help us? That helps us because of stoichiometry. So now with stoichiometry, I can look at the coefficients. I'm looking for how much CaCO3 I've got. And if I have 0.615 moles of Na2CO3, and it's a one-to-one relationship, then I know that I have 0.0615 moles of CaCO3. Easy? Yeah. Everybody on track with me? We're going back in time. All right, we've learned all this before. And then we just have to convert to grams. So I'm going to take what I know, I'm going to put it over 1, and I'm going to convert to grams. Where did I get that 100.1? Please, somebody tell me, where did I get that? Periodic table. That came from the periodic table. CaCO3. Add them all together, 100.1. Okay? So we need our chart for this, but we didn't need it for that first part right there. So therefore, I need 6.16 grams of CaCO3. All right, so we're essentially putting everything together that we've learned so far, and we found this out, which was from last module. It's not even new. It's just like a refresher. Okay. I have something else here. What do I have? Oh, yes, number of moles equals M times L. I did put my formula in there for myself. Otherwise, I forget. All right. So I'm going to tell you that up there, those formulae, that M equals moles over liters is your friend. It's so useful. You don't have to go through many more steps to get to the answer for this. Okay, the following reaction is carried out in a lab. That thing. If 125 milliliters of a 0.5 molar H2O2, and I want you to know our H2O2 reactant. This was getting me confused because look, I also have H2O2 in my over here, right, in my products. So I had to remember this isn't our reactant. So if I have that much, it's reacted with an excess of everything else, how many grams of oxygen will be produced? All right, so the thing we want to know here is we're going to go through those same steps we just went through, but look at the relationship between our reactant H2O2 and our product O2. What is it? It's 5 and 5. It's 1 to 1. Hooray. We're a 1 to 1 ratio. Okay? All right, so we're going to go through this. All right, here we go. All right. Remember, our M can help. Our molarity can help. First thing I think we have to do is make our 125 into liters. Is that right? Yeah, convert to liters. There it is. And then I'm going to just plug it into the formula now and find my number of moles. So now I have my number of moles of H2O2, 0.06. And since I know that I have a one-to-one relationship to H2O2 to O2, I know that I have 0.06 moles of O2. And I'm going to convert that. I did a little bit, I didn't mean to do that. I did a little shortcut right here. Instead of putting it over 1, I just put this over grams per mole here. Anyway, 32, where did that come from? Our 32 grams per mole from the periodic chart element. 16 plus 16 to 32. And so therefore I have 2 grams of O2. 2 grams of O2. All right, so that's essentially the same problem we just did with new data. And this might be the one that's slightly different than the one that's actually in your book. It's just some different numbers. And I just used the old, this must have been from the old book or whatever. So if you want to continue going through those as you study for next week, you can just follow those steps in there. And if you're really struggling with it, I would write all the steps down. I'd rewrite all the steps down because that'll help you not to skip a step. That's how I would study. I'd rewrite my notes. All right, yikes. All right. One way to purify a mixture of two metals, they're mixed together like an alloy, right? They're mixed together, maybe found naturally in the earth or something, is to add to the mixture something that reacts with only one of the metals and turns it into an aqueous solution. In other words, I can dissolve one of the metals and leave the other one solid. The mixture can then be filtered, isolating that metal. A mixture of magnesium and aluminum is treated in such a way to isolate the magnesium. Sodium hydroxide, which reacts only with aluminum, is added. So we see we have an aluminum, we have my sodium hydroxide. Right here, my magnesium, I guess, is not even, so we don't even have magnesium in here, right? It's not even in my, because it's not reacting. It's just sitting there. So we can't forget about the magnesium. That's what we're trying to get. But it's not in our chemical reaction because it's not reacting, get it? So it's not reacting. But my aluminum is. Here we go. The aluminum is converted to an aqueous salt. The magnesium is not part of the reaction. It stays solid. The solution's filtered. I get my magnesium. Okay, here's our problem. If a mixture of these two metals contained 1.20 kilograms of aluminum, how many liters of a 6.50 molar NaOH solution would be needed to make sure that all the aluminum was taken out? All right, here we go. 1.2 kilograms. How many liters? So we're going to use this, convert kilograms to grams, easy enough. Although we are using our scientific notation right there, which I don't know about y'all, but it mixes me up a little bit. I'd rather have my zeros. Honestly, I'd rather have my zeros so I could see them. But this is the way the book does it, so I'll do it the way the book. Are y'all comfortable with your scientific notation? Mm-hmm. You're good with it? Okay. I just don't like it. It's kind of like Roman numerals. I just don't like it. I want to see everything. All right, I'm going to determine my moles of aluminum. I'm going to take my grams that we just calculated. I'm going to do my 1 mole over 27, which came from the periodic chart of the elements, and I end up with 44 moles of aluminum. All right, so what am I going to do next? What are we asking? How many liters of a 6.5 molar NaOH solution do we need to get this to go? All right, so there's a 1-to-1 relationship between our aluminum and our NaOH. Hallelujah. It's 2 and 2, right? That's a 1-to-1. That means 44 moles of NaOH are what I need. So let's see how many liters I need. Here we go. So I use L equals moles over molarity. Very easy. Easy breezy. So we just need to remember that one equation and its derivations right there. Okay, so it's molarity, the molarity equation. As long as we remember that, we'll be gold. And practice on some of those practice problems if you're struggling with it. I just have to do them over and over again. Just do them over and over and over again. Then I get it. That's because it's not coming to me naturally. A lot of y'all have it coming to you naturally. Praise God for that. All right, now our new word. Are you ready? It's so wonderful how chemists do this to us. The new word is molality. Why can't they pick something totally different? No, they have to pick something that sounds a lot like molarity, and it's molality. All right? So, but the way I told you about molarity being your friend up here, we're going to feel the same way about molality. Okay? The difference, what's the difference? The difference is molarity is finding our liters, right? Our liters. We see it right there in the thing, in the equation. Our molality is finding the mass, the kilograms. So if we have a mass, so how much easier it's going to be? What if I'm dissolving salt into water? I don't have liters of salt. I have grams of salt. All right? So it makes much better sense to when we're talking about solids and stuff to be using molality. But it is a concentration. It's just the same thing as molarity is concentration of the solution. The molality is also the concentration of the solution. I'm just using kilograms instead of liters. Yes? Easy? See, that's the only big new thing you're learning in this whole module. And all it is I'm using grams. Kilograms. And kilograms is important, by the way. We have to use kilograms. So the equation calls for kilograms. All right. So for molarity is concentration is moles over liters. For molality is the moles of solution over the kilograms of solvent. And this is used with freezing point depressions and boiling point elevations. I have those underlined. Are you supposed to write that down? It helps to define how much solute can be added to change the behavior of a solvent when cooling it or heating it. And I think I do want to write down that formula. It is. Also notice molality, it's a small m. It's a lowercase m. It has to be the lowercase m so you don't get it mixed up. M equals moles over kilograms. All right? Moles over kilograms. All right. A chemist mixes 3.4 moles of sodium chloride with 4.5 kilograms of water. So far I'm liking this. I've got kilograms and I've got moles. Okay, good. What's the molality? This is, hopefully, you'd have 10 questions like this on the quiz next week, and you'd be happy. Okay, because what am I going to do? I'm just going to plug them in. I'm going to say molality equals moles over kilograms. There it is, 0.76. Little m for molality, little m. So 3.4 moles of NaCl divided by 4.5 kilograms H2O is 0.76. Molality, the solution has a molality of 0.76, little m. Easy breezy. May not even use your calculator for that one. All right. Okay, so now freezing point depression. So what does that mean? What does freezing point depression mean? When the solute is dissolved into a solvent, it always lowers the freezing point. The attraction of the molecules in the solute add energy. This means that more energy must be removed to cool it. It gets real almost philosophical in your book, talking about as I'm putting that in there and adding that energy, therefore I have to put more energy to cool. If I cool it down more, I can take more of that out. Just read through that. It's more of a philosophy of chemistry. It's true. It's not untrue. It's just we don't really care. I don't care why it does. You ever had that? I don't care why it happens. Just tell me how to do the problem, and you know. But if you know behind it what's going on, it'll make sense to you. So as I started to grow up, when I was like at work and stuff, I would say, well, just tell me how it's working, and then I'll know more instead of just why and how to do the problem. Okay, but that is right there what's going on. So let's see. If we add salt to water, it will lower the temperature to freeze the water. Okay, it'll take more to freeze it. So like in the streets. Now we don't have this much down here where we have to salt the streets. So my husband grew up in Wisconsin, and they had snow for, I don't know, 7 months out of the year, 9 months out of the year. Is awful. That's why I moved down here. And so what they had to do was, when the streets were so full of mostly ice, you can't drive on them, and so they put this solute into the ice, a solid salt, and it causes the ice to go away. Okay, and that has to do with adding the salt to it. The sad part is the salty, snowy stuff would splash up on the undercarriage of all the cars. So if you've ever seen a car that's all rusted on the under part of it right there, that car came from up north somewhere where they use salt on the roads. Around here, I don't know, I guess we do have some sort of solute that we use in really, really tough times, but mostly what we do is put down friction, and we put down sand or something like that. All right, let's watch a little video.
Now that winter's here, the weather fiends out there are waiting for the next big snowstorm. But before the flakes fall, armies of trucks are loaded full of one of the most important road safety tools out there, salt. And along with keeping our french fries on point, salt, like sodium chloride, has actually saved a lot of lives and probably even more fenders thanks to its incredible de-icing abilities. So here's a truck throwing salt all over some wintry road out there. And like everything else in the picture, you can bet the salt is pretty cold. This begs a question. How could it be that something that isn't hot is melting the ice? Turns out salt isn't actually about melting. It's all about freezing. So the freezing point of pure water rests at 32 degrees Fahrenheit or 0 degrees Celsius. When the temperature of water reaches a freezing point, its normally free-flowing molecules get trapped into organized crystal structures. This is how ice is formed. Salt disrupts this process. Upon hitting water, salt breaks up into two ions, one sodium and one chloride. These two ions then move around and take up space in between water molecules, pushing them apart and frustrating their potential links to form ice. This disruption is called freezing point depression. And so to put this simply, salt lowers the freezing point of water. But there's a limit. Salt can only act as a stable de-icer in temperatures above 16 degrees Fahrenheit or -9 degrees Celsius. And there's also another drawback to using salt. Considering that over 20 million tons of road salt is used annually in the US, all that salt has to go somewhere in the spring. Of those two ions split from dissolved salt, the chloride ions can have a potentially negative effect on the environment. Chloride can kill small aquatic critters, dehydrate and kill plants, alter the composition of ground soil near roads, and can limit water circulation that keeps lakes healthy. All that salt is also corrosive to metal, wreaking havoc on infrastructure, and oh yeah, your wheels too. For these reasons, sand is used as an abrasive as an alternative. Sand is often used because it's cheap, and maybe because folks want to avoid the whole chloride issue. Thing is, salts have a chemical advantage. Because you get two or more ions when they dissolve, you get way more melting power for the same handful of de-icer. So sand might be cheap, but you have to use way more of the stuff, and that can leave quite the mess. Now, for super cold temperatures, sodium chloride and sand won't do the job. Some alternatives that melt ice even better include magnesium chloride, calcium chloride, potassium chloride, and potassium acetate. Potassium acetate is particularly incredible at de-icing because it works at temperatures as low as -75 degrees Celsius, while the rest of the bunch work around the -20 degree mark. Although these alternative chemicals are better at de-icing at lower temperatures, most of them have that environment-damaging chloride too, not to mention the fact that they cost way more than table salt. And if you're buying 20 million tons a year of this stuff, well, that's a lot of money. So people, keep your eyes on the road and thank salt for the fine driving conditions. Or on the other hand, you can shake your fist at it if you don't get the snow day that you deserve. Make sure to...
Yeah, so we might have some weather this weekend, turns out. It wasn't supposed to be here till like Thursday, but it wasn't supposed to be this cold today. So it came sooner than it, because it's not, this is about as warm as it's gonna be today, I think. 56 or 57, something like that. Or later this weekend, it might be some snowy mix on Friday or Saturday. So we might build some more snowmen. Yeah, cool. All right, now this is kind of fun. These are guys who did their own little freezing point depression lab, like a science fair project. Which reminds me that we are going to do our own little, just campus-wide science fair here. All it will be is if it's not required, it's optional, but it will give you extra credit for this class. It'll wipe out a bad quiz grade, and it'll just knock out, like if say you got a 0 on a quiz, it'll make it a 100. That'll really help your average right there. And so you'll have to present it to our class during one of our lab times. Just stand up with your board and tell you what you did, some sort of chemistry thing. And then for the rest of the deal, you just have your board out there and other people will get to look at it. And it's possible, I don't know if they're handing out ribbons or not, but you know, you can always, anybody doing 4-H? Anybody doing 4-H? It's just, or how about when you do your, what do you call that? Resume for college? You can put it on there that you were in a science fair and you got a ribbon. You see, all that counts for something, towards something. So think about it. And watch what these guys did. They're kind of fun.
Today we're going to do a demonstration on freezing point depression and the dependence of viscosity of a liquid on temperature.
I think the sound gets better.
So as you can see here, we have a regular plastic Tupperware box. It's filled with 12 full half-liter water bottles. It's fairly heavy. It weighs in at about 14 pounds total. We have a glass Pyrex piece of bakeware. We've got some ice, some honey, and some table salt, which is half sodium chloride and half potassium chloride. We're going to begin by placing some honey on top of the Tupperware box.
So that's honey.
Next, we're going to place the glass on top of it.
Gotta stick it to it.
Then we'll pour in some of the ice. And finally, we'll add some water. The water in this demonstration is at room temperature.
All right, ice water in the tray, nice and cold. Honey underneath it.
Now we're going to set a timer for 2 minutes, and once the 2 minutes have expired, we're going to try to pick up the box by the handles of the box ring.
They're playing tic-tac-toe. 2 minutes.
It is evident from this demonstration that the honey is nowhere near strong enough to lift the box.
So now I think they're magnesium chloride. Adding some honey. So when the honey gets really cold, you know this, right? It doesn't flow as easily. It's less viscous. So they're going to change the viscosity here.
At this point, we'll add in a large quantity of table salt and stir the solution. We set the timer for another 2 minutes, and once these 2 minutes have expired, we'll again try the test.
Any guesses?
This time, the honey is strong enough to support the weight of the box.
Pretty cool.
Let's now take a look at some of the chemistry behind this demonstration. The freezing point of a solution is called a colligative property, which means it's dependent on the molality of the solution. The molality of a solution is calculated as the number of moles of solute divided by the kilograms of solution.
We knew that.
The change in the freezing point of a solution is given by K sub F times the molality, where K sub F is a constant intrinsic to the solvent. When we lower the freezing point of a solution by adding salt,
Okay, I'm just gonna move on because we can't understand it very well. Okay, and I'm gonna talk about this. So what he was saying was completely correct. All right, so with that freezing point depression, we'll also look at the boiling point as well. So we're gonna see here, there's a new formula. Is this written down for you? If you want to wait till I have it bigger, you can. I'm gonna have it bigger in just a minute. Here's both of them. We're gonna put those in. What I do want you to know, I'm gonna go ahead and write them down for you right here. Delta T. Where can I put this? Right here. Delta T. When you see that delta, that means change in temperature equals negative I. Okay, with F and M. So we'll start with that one. That's our freezing point. 1. So we see our negative there. Think about freezing negative right there. I is interesting. Okay, so that little I that's in there, listen really closely right now. Stop writing and listen very closely. I is the number of molecules or ions that the solute will split into. That's what the solute will split into when it dissolves. Ionic solutes split into separate ions. Covalent solutes stay as one molecule. They do not split up. Think about that sugar we looked at. It'll stay as one big molecule. And in that particular case, if it's one big molecule, I will equal 1. But sodium chloride, it's sodium and chloride, I would equal 2. this is also important to remember our polyatomic ions when that happens. Okay, all right. Next, the Kf is the freezing point depression constant. It will be given to you. All right, it comes from a chart somewhere. It'll be given to you. The Kb will be the boiling point elevation constant, also a given. And then little m, of course, means molality, number of moles of solute over kilograms of solvent. So let's start with freezing point. Here is that larger, where you can see it a little better. Delta T equals negative I times the constant K to the F, freezing, times molality. So when a solute's dissolved in a solvent, the solution always has a lower freezing point than the pure solvent. We mentioned that earlier. It always does. Because it makes sense. It's going to get in between those water molecules. Okay? So this is the formula we're going to use now. So even though we have this lovely easy molality thing up here, we probably don't use that very much. We're going to use molality in these, which is a little more, right? Okay, so let's see. We're going to practice now. When 15 grams of sodium chloride are added to 100 grams of water, what is the change in the water's freezing point? And right here you'll see my Kf of H2O is 1.86 degrees centigrade over M. So now what we have to determine is we have to determine molality, M, and we have to use that, and we have to determine I, which is what will the ions break into, okay, or not, right? So first thing we're going to do is find our moles of sodium chloride, so I can go to my moles for my molality, get it? Right? Remember, I still need my number of moles up there. Okay. So I'm going to get my moles. I'm going to find my 15 grams. My 58.5 grams of NaCl comes from the periodic chart of the elements. That's just converting grams to moles. I have 0.256 moles of sodium chloride. Here I'm going to take my grams and make them kilograms. That's important. And now I can do my molality. So my 0.256 moles, which I calculated, over my kilograms of water, 0.1, is going to give me a molality of 2.56. Molality of 2.56. So now I've just figured out M. So I've done step 1 of our calculations here, just step 1. And now we have so we have M. We have Kf, we have M. We need to find I, and then we are looking for delta T. We're looking for T, right? What is the change in the water's freezing point? And you need to understand what water's freezing point is without anything in it, which is 0, right? 0. All right, are we good? Can anybody figure out what do we put in there? Sodium chloride, what's I going to be? It's going to be 2, sodium and chloride. Okay. All right, I just wanted to point to that M is going right up there to molality. Okay. Now to find I, think about how sodium chloride dissolves. Since it's ionic, it will dissolve into 2 separate ions. So I will therefore equal 2. So now I can plug everything in. Delta T equals negative 2. Where'd the negative come from? It's in my formula. It's in my formula. Okay? Negative 2 times 1.86, which was given to me. That was a constant. Times 2.56 molality, which we calculated, will give me negative 9.52 C. Everything's going to cancel out there, and I'm going to be left with my degrees centigrade or degrees Celsius. The negative means that the freezing point lowered, so the freezing point of the sodium chloride solution is 9.52 degrees lower than the freezing point of water. Okay, so there's my number. It is negative 9.52. That means that it won't freeze instead of 0, it's going to freeze at that minus 9, so about 10, right? So negative 10. Get it? And that thing we just watched, that was happening inside the Pyrex dish. That's what was happening there. The honey was almost incidental because it was just making it more viscous. But it was just showing how cold it got, how much colder it got. All right, in order to prevent the water in a car from freezing, this is real practical right here, we add antifreeze. It's C2H6O2. That sounds like a non-ionic thing right there, right? That sounds like must be a polar covalent. To the radiator. What is the freezing point of a radiator solution made from 4.00 kilograms of water and 1.00 kilograms of the antifreeze? That's C2H6O2. And we're given our Kf right there as 1.86. All right, so where do we start? Oops. We're going to convert grams to moles so we can get our M. Okay, we're gonna go for our M first. So I can do all this with the numbers that I have, the number from the chart. I get 16.1 moles. And now I'm going to find my little m, molality, 16.1 divided by 4 kilograms. Was it already given to us in kilograms? Yay, yes, it was. So my m is 4.03. All right, next I have to do I, right? Figure out I. C2H6O2 is not an ionic compound, is it? So it's not going to break up into little parts. It's going to stay 1. So it's going to equal 1. Do you get that? It's just going to equal 1. All right, now I can plug everything in. I have my -1, my 1.86 was given to me, my KF up here, the 4.03 I calculated, and my answer is -7.50. That means that it is going to have to be that much colder before my engine will freeze. You'd think it'd be a little more than that. Yeah, so -7.50. Doesn't seem very impressive. It's only 7 degrees, you know, but. All right, so it's just tedious math work. Yeah. I think y'all are probably taking math somewhere else, aren't you? Taking your own math class? Why do we have to have it here too? All right, boiling point elevation. Here it is. It's very similar, except notice my I is positive here and my K is KB. When I solute is dissolved in a solvent, the boiling point of the resulting solution is higher, which I think we already wrote that down. All right, so now we're going to use this. And this gets a little more in my book. Well, the antifreeze one's pretty practical. But we're going to use one now where we are going to add salt to cook pasta. We're going to cook some pasta. Y'all cook pasta? You put salt in there? Yeah. It's because salt tastes so good, right? It actually allows the water to boil at a higher temperature, therefore to cook faster. The chef adds 20 grams of table salt to 1.45 kilograms of water, brings it to a boil. What is the temperature of this solution? And then our KB is given to us right there at 0.512. All right, first thing we're going to have to calculate I and M. Let's go ahead and convert to moles so we can get our molarity. Molality, see I did it just then. Molality is what we're looking for. All right, we're going to do our 20 grams, put it over 1. We're going to find our 58.5 grams of sodium chloride in 1 mole of sodium chloride. That is from the periodic chart of the elements. And I calculate out that I have 0.3 moles of sodium chloride. And now I can calculate molality by putting that over the kilograms that I had. Yes, I already had kilograms of water, so I have a molality of 0.2. Now I'm going to go figure out my I, right? NaCl, yay, that's 2. It's going to split into 2. So my I is going to be 2. And then I can put it into this formula right here, and I'm going to see that I'm going to end up with 0.2 degrees. So that salt in my water only brought it up 0.2 degrees? Doesn't seem very impressive to me. I did watch a cooking show this weekend, and the guy was talking about that you should, and I've heard this before, that when we're putting the salt in our water for our pasta, that the water should be like the ocean. In other words, really salty. Really salty. So add more salt. Maybe it'll really cook it that much faster. I also put it in boiling potatoes when you're getting potatoes ready for mashed potatoes or whatever. Salt in there. All right, so not very fun. Oh, since water boils at 100 degrees C, the new boiling point is 100.2. I don't even know if our thermometer would be sensitive enough to pick that up, that difference right there. But that's the practicality of this one right here. All right, acetic acid. Okay, we're doing something besides water and salt. Here we go. Acetic acid has a Kb of 2.93 C/m and a normal boiling point of 118.1 degrees C. What would be the boiling point of a solution made by dissolving 50 grams of calcium carbonate in 500 grams of acetic acid? We see we have to change that already right there. But what do we know about calcium carbonate? Tell me about this molecule. It's got a polyatomic ion in it. CO3. It's a polyatomic ion, right? It's called carbonate. We got to remember that. So what's our I going to be on this one? I'm going to calculate that I. What's it going to be? 2. Calcium and then the carbonate. Okay, good, good, good. All right, let's go through it though. Let's slog our way through it. You know, I love these math problems. Are y'all happy that none of these were on the recording, so I couldn't play the recording for you? Would you prefer me to do it rather than the recording? Really? My problem is when I feel like I'm going to miss something if I don't have the recording. Okay, so I had 50 grams of calcium carbonate. I'm gonna convert that into moles. Here it is. My number on the bottom right there came from the periodic chart of the elements. Therefore, I have 0.5 moles of calcium carbonate. Now I'm gonna find molality, right? Oh, I gotta convert kilograms to 0.5. That's easy enough. Now my molality, 0.5 moles of calcium carbonate over 0.5 kilograms of acetic acid. That all equals 1? Oh, yay, I love ones in math. Those are my favorite, those besides zeros, right? Calculate the I, it's 2. We understand why it's 2, calcium and then the carbonate. And our delta T is 2 times 2.3, which was given to us. Yep, right there. Times 1, which we just calculated out. So it's 5.86 degrees higher, and the boiling point was normally 118. So I add that together. That says equal, but it should be a plus sign. 124. So now it's going to boil at 124. That seems more impressive. I put this in here to remind us that that is carbonate polyatomic ion right there. Okay? Hey, we're done. All right. So see, it's not that bad. It's not that bad. Practice some of those boiling point depression and freezing point depression and boiling point in your practice problems. All right. Julia, do you have a quiz for me?
No.
I just sent it to you yesterday.
Yeah, I was
Okay.
on the planes. I didn't get time.
Oh, that's you just got back.
Yeah.
I think I have one for you, and I had a question. You sent me one,
Yeah.
and then, but I didn't know if you did your study guide for it.
Oh, yeah. I forgot to bring it. Could I bring it to you next week?
What, the study guide?
Yes.
Okay, so you may just keep this. You can see what you got, and so that'll turn into a 90 if you give me your study guide. But let me keep it because if I don't keep it, I won't change it on the computer, and that's where it matters. Okay. So let me keep that till next week.
Bye, Miss Garcia.
All right. See y'all next week. Or so.
So long.
Okay.